Greetings and welcome. So this video is titled Sliding Down a Slope, a symplectic symphony of Hamiltonian horrors. So who are these horrors for? Who is the intended audience of this video? Well, I reasoned that it would be very nice to have a simple example such as a block sliding down a slope when dealing with a difficult topic such as symplectic geometry. So this video is sort of the video that I would have wanted to see when I was first learning the topic of symplectic geometry. Unfortunately, it wasn't available at the time, but you are slightly more fortunate, well, assuming, of course, that you are indeed the intended audience. So first of all, what is our problem? A sled of mass m slides down an incline of alpha degrees, starting at rest at a height of h. Given a constant friction of f, what is its position and momentum after t seconds? So, simple enough a problem. We have a slope, we have a little block there, we have alpha degrees, and the h is the height over here. And we have a gravitational force in the direction of the slope, mg sine alpha, pretty standard, and a force acting in the opposite direction. And obviously it's very simple to solve from here. I mean, I already projected the force along the direction of the incline, but we aren't going to do it that way because we're trying to learn some symplectic geometry here. So we're starting out instead with the Hamiltonian G-space, m omega g h, and we're going to unpack that. We're also looking at the principal G bundle here. So G is a group, pi is a projection map here from the manifold to the quotient space M quotient G. So in this case, the fibers are the G orbits, and pi is the projection map down along them. The symplectic manifold in this case is going to be R2 times R2, and these Q's are obviously the positional coordinates and the P's the momentum coordinates. So this is a standard phase space, not all that tricky, and people will have seen those in undergraduate courses on a fairly basic level. And I'm going to put the QX direction here and the QY direction here, and I'm not drawing the PX and the PY in this picture because they're not positional coordinates, they're momentum coordinates. And we have a canonical two form, a symplectic two form, and that's simply going to be the symplectic area here, dqx wedge dpx, dqy wedge dpy, and this is a two form, so I write sections from alpha to the second exterior algebra of the cotangent bundle. Now, symplectic two forms, they induce Poisson brackets. And this is an example. If f and g are functions on the manifold, then the symplectic two form for the Hamiltonian vector fields associated with those functions will be the Poisson bracket. So that's how we can go from symplectic two form to Poisson brackets. Now the xf, the xg here, they are such that, for example, with an xf here, it's going to be the vector field such that the interior product along that vector field with the symplectic two form, it yields the differential of the function, the exterior derivative of the function. The canonical one form, that's this symplectic potential here, theta, it's going to be px dqx plus py dqy, and you can easily verify that it's such that if we take the exterior derivative of it, we get the symplectic two form with a minus sign. And this exterior derivative here is from k forms to k plus 1 forms, the usual exterior derivative. Now, one can certainly consider other choices of canonical one forms. Anything that differs from theta by an exact form will also be a potential. As for the G, that's our Lie group action, and it's isomorphic to R2 in this case because I've chosen spatial translations to be our symmetry group. Now, there are obviously more symmetries to a problem like this, but I decided to focus on the spatial translations because they're quite simple, and if you're familiar with symmetries in physics and Noether's theorem, you will know that spatial translations are associated with a conserved quantity that is known as momentum. The H is, of course, the Hamiltonian. It's a Hamiltonian G-space. They have a Hamiltonians. And here we have a kinetic term. This is just the square of the momentum over 2m plus a potential term here. This is the potential energy associated with gravity. So it's mg times height, qy. And I also need a term to absorb the energy associated with the friction here, because we have a constant friction of F, and so the friction is doing work on our little block here, and one could consider this term as being the change in internal energy of the block associated with the work done by the friction. The x in this case is just the distance this block has slid. So I could write the x with the Pythagorean theorem if I want. Square root of this height here minus the qy to get this little distance here, plus qx squared, the distance to the side here. But I'm not really going to be using that expression all that much. What I'm going to do is that I'm going to decompose my g into a g psi and a g psi perpendicular. Now the psi's here are going to be elements of the Lie algebra, but in a vector field representation of the Lie algebra element psi, I'm going to write this as a del qx plus b del qy, and a and b are simply such that we're pointing out of the plane here. So this is perpendicular to the plane. Now, obviously, I could have written a and b explicitly, such that they are perpendicular to this plane, but I saw no reason to do it, and just left them as a and b. So rho is something representing the Lie algebra here as a vector field. So it's from the Lie algebra G to sections of m to tm, tangent manifold. And this G here is the Lie algebra of the capital G. Constructing a moment map now. So a moment map is something mu from m to the dual of the Lie algebra. And in my case, I want a moment map with respect to this partial Lie algebra. I've decomposed my group. I want to do I want to create a partial moment map here. And G subscript psi is the Lie group of G subscript capital G subscript psi. And if I pair this mu with psi, that's just a function on the manifold, and I can create these moment maps with a very, very common technique that's very, very handy. It's a way of constructing conserved quantities. I take the interior product with respect to this vector field here, with the symplectic potential here. And this was the vector field, and this was the symplectic potential. And this is basically just a scalar product at this point. So this will pair with this, and this will pair with this. Interior product with respect to del q with the qy here, for instance, it's not going to produce anything. So the surviving terms are these, and this is just the momentum in the direction perpendicular to the plane. As for that matter, the theta could be seen as a Lie algebra valued one form if we consider the Lie algebra that is not this Lie algebra, but rather the Lie algebra that is the functions on m along with the Poisson bracket, which is a very important Lie algebra. And that would then, of course, have a curvature, fxy, sectional curvature with respect to the vector fields x and y. And that means the commutator of the connection along x, this should say commutator along y. Don't know why I wrote x there. Obviously, that's not right. Minus the connection along the Lie brackets of the two vector fields. And this is just d theta plus theta wedge theta. And this will vanish in this case, but in the case of a more interesting Lie algebra, say for instance the Heisenberg algebra in quantum mechanics, when we replace the Poisson brackets with the commutator, this might not always be vanishing. It's still going to vanish with a really trivial one form such as this. So in that case, we will still get this minus omega contracted with x and y. This is contraction with x and y. And the connection is defined as d plus theta gauge potential. So that's a bit of an aside, just to talk a bit more about what these gauge connection forms are good for. What we're really trying to do here is a bit of symplectic reduction. The symplectic reduction will be partial. It will be with respect to these psi's. We've created a partial moment map, and we did that with a symplectic reduction in mind, where we're going to take the pre-image of this 0 right here and quotient it with the group G psi. And this means all translations along the direction perpendicular to the plane. And what this means, well, what does this mean? Well, this mu here, that was p psi, right? So we're looking for everything really with a p psi that is 0. That is to say, every point on the manifold with a p psi that is 0. So all points qx, qy, px, py on the manifold such that this scalar product here gives us 0. Now, this is clearly just a line in momentum space, so I can trade out my R2 to an R, because I've lost a degree of freedom, quite simply. And that's the degree of freedom in this perpendicular direction here. But in the momentum space, not in the positional space. Nothing happens to the position space. On the other hand, I'm now quotienting this with G psi, but we said that G was spatial translation, so it acts solely on the positional part of the manifold. So when we quotient back G psi, we reduce the degrees of freedom on R2 by 1. And so we get R times R as our final manifold. This is our reduced manifold. And we can see here that we really did need to perform this quotient at the end, because this sphere is three-dimensional. Symplectic manifolds are not three-dimensional. They don't have symplectic structure, so we can't do symplectic geometry. Now, we need a function here from the reduced manifold to the manifold, because those will induce pullback maps on our forms. So the pullback maps, they will be from forms on the cotangent bundle, so sections from M to the exterior algebra of the cotangent bundle to the corresponding forms on the cotangent bundle on the reduced manifold here. And I'm considering something like f like this, where we go from x and p, going to let x just be this x, and the p be now the one-dimensional momentum of the reduced manifold. Then it's fairly simple to write the qx, the qy, the px, and the py because the x, if I want the qx, I'll just project it in the qx direction, multiply by cosine alpha. To obtain this qy, I will have to make reference to h, but I think you'll see if you look at the picture that the qy is just going to be h minus x sine alpha. And similarly, for the momentum in the px direction, we're going to have p cosine alpha, and in the py direction, we're going to have minus p sine alpha. And I can use this to pull back my Hamiltonian to this reduced manifold here. So I'm writing h hat here for the pulled back Hamiltonian, and this is f pull back the old Hamiltonian. Now this was just x, so I can just write that x here. As for px squared, well, that's this squared, and py squared, that's this squared, comes to that, and because of the trigonometric unity here, we'll just get p squared out of this factor here. As for the mgqy, I'll just use the formula for qy here, and this term becomes mg parenthesis h minus x sine alpha. So with that slight simplification with the trigonometric unity, I get this expression, which is a lot simpler. Now, obviously, I could have started here or somewhere else, but the point was that we wanted to practice our symplectic geometry, so that's why we wanted to perform a symplectic reduction, a Marsden-Weinstein quotient. Now, clearly, those are useful for a lot more than just reducing the dimensionality of problems where we aren't using all dimensions that we have available to us. Like in this case, we have a plane, but we have an object that only moves in one direction because of constraints. So we could do it that way. But in other cases, we might have some redundancy that's associated with the gauge group of a quantum system or something. So there could be quite different scenarios where Marsden-Weinstein quotients, symplectic quotients, are so useful. As for right now, we're just going to continue by pulling back the symplectic form as well. So the symplectic form was this, standard Darboux basis symplectic form, d qx wedge dpx plus dqy wedge dpy. And I can write these exterior derivatives now, pulling them back one by one using this function here. So qx, I'll just use this expression, differentiated by x, and that with dx plus that with dp will all together just be dqx, right? This is the differential of dqx. And then I need to wedge that with dpx, and all of this is just dpx. And then this term is the dqy, and this term here is the differential of dpy. And before I even use my function and look at what the qx, for instance, is explicitly and all of that, I can note that there's some simplification to be had here, because, say, for instance, dx wedge dx doesn't yield anything. So what I have left, and you can pause the video and check for yourself, will be this, which is not that much. And these are quite simple to compute. The del qx del x, that's this differentiated by x, so cosine alpha. And then del px is this one, differentiate with respect to p, and get this one. And similarly for qy and py, and so we get this. And in the end, it turns out that our entire symplectic form pulls back quite simply to dx wedge dp. Now I have my new Hamiltonian, looks like this. I can compute the differential with respect to that Hamiltonian, just differentiating by p, right, and writing a dp there, differentiating by x, writing a dx here. So this is the differential of the Hamiltonian. And now I'm in a position to compute the time evolution of the system. Because the time evolution is given by the Poisson brackets with the Hamiltonian. Not just for coordinate functions like an x, but for any function on the manifold. As long as it's sufficiently nice that we can actually produce a Hamiltonian vector field for it and all of that. So x dot time derivative of x is Poisson bracket of x with h hat, which is omega tilde. That was our new symplectic form with respect to the Hamiltonian vector field of x and the Hamiltonian vector field of h hat. And as we saw in the formula in the beginning, this is interior product Hamiltonian vector field with respect to x on the differential dh. That's why we computed this dh hat here. And all of this will, if we take this minus del p here, you can see that this is actually precisely what is going to produce a function x if we take this interior product not with respect to dh hat, but with respect to the symplectic form. That's what makes it the Hamiltonian vector field of the function x. So it could be, if you haven't seen that before, I would advise that you look into the Hamiltonian vector fields of coordinate functions, whether they're spatial or momentum coordinates. So del p with dh hat, obviously that picks out this term here, will give nothing with dx. So we get minus p over m, or the time derivative of x is minus the momentum divided by m. Different sign than we're used to, but that's fine. P dot will similarly be the Poisson bracket of p with h hat equals the symplectic form xp x h hat, and this equals the interior product again, but with the Hamiltonian vector field being the one with respect to momentum, and that's just del x. So this is going to pick out this term here, which we might recognize as the net force on that block. And that just comes to this, and saying that the time derivative of the momentum is the net force is sort of familiar, isn't it? That's Newton's second law. And we have all we need. I can differentiate the first equation with respect to time, and I'll get minus p dot over m, and then I plug in my expression for p dot from the second equation, and I will simply get this. So what the claim is now that the acceleration is g sine alpha minus the force of friction over m. And integrating once, this is a constant, so just getting a t here and an integration constant. Integrating twice, get another integration constant, and this is now t squared over 2, this is ct. And we plug in some initial conditions. In the beginning, we were up here, so x of 0 was 0, and we started at rest, so p of 0 is also 0. And plugging that in here will quite easily see that c and d need to be 0, and we arrive at our final solution. X of t equals g sine alpha minus f over m, t squared over 2, and minus p of t equals mg sine alpha minus f times t. So I can just plug in values of t here, and I will have my position and momentum, which was the goal of the exercise. Again, the sign of p is slightly unconventional, but that's not important. So let me know what you thought about the video, if you thought that this was an interesting way of doing it, or if some questions arose. I would be interested to hear what you think.